Hello everyone, welcome to today's lesson on the GCF and LCM, or the greatest common factor or least common multiple. It will seem like a lot of work, but it's pretty much just the same method repeated over and over again. But before we do anything though, here's the most important definition here. Right, a prime number is a number that can be only divided by 1 or itself. Right, so things like 2, right? 2 is only divisible by 2 or 1. Or it's number 7, right? It can be only divided by 1 or 7. 4 can be divided by 1, 4, and also 2. Right? So 4 is not a prime number. So yes, if it's an odd number, chances are it might be prime, but you have to check. Right? So if you're curious, 1 and 0 are not prime numbers. Right, so 1 and 0. Okay, next the prime factor. Right, so a prime factor is pretty much a factor that is prime. Right, so if we remember, factors are essentially the numbers that multiply to a bigger number. And if that number is prime, then it's considered a prime factor. And lastly, prime factorization is writing that big number as a product of all the prime numbers. If this all seemed like gibberish to you, right, no worries. We have pretty much a page and a half of all examples to get you familiar with all this. Okay, so one of the most important skills in math is figuring out what the factors of a number are, or more importantly, what the prime factors of a number are. Because prime numbers are pretty much just building blocks, right? We put a bunch of those numbers together, and we multiply them, and that's how we build bigger numbers. So it's important to know what is at the base, what's like the foundation of those numbers, so we can do some pretty cool stuff with them. Let's take 12 here, right? So starting with 12, let's take two factors, so two numbers that multiply to 12. I can take, let's say, 3 times 4, or 4 times 3, doesn't matter. Okay, and then we draw two branches, right? That's why it's called a factor tree. We're just drawing branches like this. Now we check, are those prime? 3, right? 3 is a prime number. It is divisible by 1 and 3. That's it. And next, we'll check 4, right? And as you probably know, or in the example earlier, right? 4 divisible by 1, 4, and 2, which means that's not a prime number yet. So we keep going, right? We keep breaking down numbers into the prime numbers. So we know 4 is 2 times 2. And from that point, we realize, hey, now 2 is a prime number. And then we're done. So at the end, 12 is 2 times 2 times 3. Okay, so all the prime numbers, those are now called prime factors. Right? Because 12 is made up of 2 times 2 times 3. And of course, we can express them as exponents. And that right here is called a prime factorization. Okay, so all we're doing here is finding out all the factors that are prime numbers, and then we multiply them together with exponents, and that's it. That's prime factorization. Let's check 40 here. 40 is 4 times 10. Okay, of course, neither of those are prime because they're even. 4, once again, we can break it down to 2 and 2. 10, we know is 2 times 5. Okay, so at this step, well, I guess at the first step here, that's not a prime number. But here, those are all prime numbers. So 40 is 2 times 2 times 2 times 5, or 2 cubed times 5. Okay, just like that. 243. Okay, it's not divisible by 2, so we can check 3. Right, 243 divided by 3 is 81. Perfect. Okay, and we know 81 is just 9 times 9. 3 is prime, so we leave a D. 9 is 3 times 3. So right here, we end up getting 5 of those 3s, right? So those are the prime factors. So 243 is just 3 to the power 5. Okay, that's it. How about 32? Well, that's 8 times 4. 4 is just 2 and 2. 8 is 2 times 4. 4 breaks down to 2 and 2. So similarly, 32 is 2 to the power 5. It actually doesn't really matter what number you pick first, right? If you realize, oh, instead of 4 times 8, it's also 2 times 16, right? We can still get our factor tree from here. 16 we know is 8 times 2, which is 4 times 2, which is 2 times 2, right? So it's also 2 to the power 5, right? So it doesn't really matter how you divide it, you'll get to it eventually. 154. We know right away because it's even, it has to be divisible by 2. Divided by 2 is 77. And from there, yes, it's odd, but we know that 77 is divisible, or can be divided to 7 times 11. Okay, 7 and 11 both primes. 2 times 7 times 1, 11. Okay, last one. Okay, 3,300. So we know right away we can split that into 33 and 100. 33 is just 3 times 11, both primes. 100 is 10 times 10, or 2 times 5 for each of those. So we got 2 2s, 1 3, 2 5s, and an 11. So 2 2s, 1 3, 2 5s, and 11. Okay, that's how we do factor trees. We just keep dividing it until they're all primes. Or in other words, keep dividing until you can't divide them anymore. Okay, so now what's the greatest common factor? So the greatest common factor, you probably see this a lot in say fractions and stuff. Right. The greatest common factor is the biggest integer, or the greatest integer, that divides into all numbers. Right, so given a few numbers together, what's the biggest number that can divide into both numbers, or more, all those numbers that we provide? So what we can do is we can list out all the factors. So 138, for example, those are all the factors of 138. Because we got 1 times 138, 2 times 69, 3 times 46, 6 times 23. So those are all the numbers that multiply to 136, or 138. Then we can do the same for 198. And now from here we can see, okay, the biggest number here is 6, right? Because both of those numbers have a factor of 6, and that's the biggest factor, right? We have 1, 2, and 3, but 6 is the biggest. So the greatest common factor is 6. But of course we're lazy. So maybe lazy is not the right word. We're efficient. So instead of writing all the factors out, we do factor trees. So 138 is even, so it's divisible by 2. Gets 369. That's divisible by 3, which is 23. Okay, and we're done. Alright, 23 is not divisible by anything. Okay, 198. Divisible by 2, that's 9, 9, and 11. Oh, and yeah, 2, 9, and 9, which is 9 and 11, and 3 and 3. So the prime factorization is 2 times 3 times 23. And 1, or 2 times 3 times, square times 11. Right? But in this case, I'm actually going to write out the 3's like this, just so it's easier to illustrate this. Okay, and now we can look at the prime factors. Right? We notice both of those have a 2 and a 3 that's in common, which means that the greatest common factor is just the prime factors that they have in common, which is 6. Right? So it's much, much faster. So we just look for all the prime factors that the numbers have in common and multiply them. Okay, let's just exercise this. Okay, 42. That's 7 times 6. 6 is 2 times 3. 84. We can do 2, and then 42. And then 42 can be broken down into 2 and 21, which is 3 times 7. Okay, so 42 is 2 times 3 times 7. 84 is 2 times 2 times 3 times 7. Okay, let's see what factors are in common. We both have a 2, we both have a 7, we both have a 3. So we multiply all that all together. To get 42. Okay, which means that the greatest common factor is 42, right? 42 can be divided into 42 and 84. And that's the biggest number. Okay, try another one. 81 is 9 times 9. It's a bunch of 3's together. 216. Right, that's divisible by 2. 108. Divide that by 2 again. 54 is 6 times 9. Okay, I gotta skip some steps here. Okay. So from here, we can try to look at all the factors in common. We got a 3 here, another 3 here in common, and then a third 3 here in common. Right, because right, at this point, we have another 3 here, but there's no more 3's to, you can see that's in common. So we just multiply, whoops, all the common factors, which is 3 3's, you get 27. Okay, cool. And of course, it works for as many numbers as you want. Okay, so let's try this. So we know that's just 10 times 15. Right, so this is why we did so many factor tree practices earlier. Because like I said, it makes this process a lot easier. 1042, 25, 67. Okay. So what do we have in common? Got a 5 here, 5 here, and 5 here. Alright, so very important here. It has to be common all the numbers involved. Right, because yes, we have another 5 here between those numbers, but with 420, there's no more 5, so we cannot take it. You can see we got 2 and a 3 here, but we have none of that in 275. So this is just simply 5. Yeah, and yeah, if not, there's nothing in common, then it's just 1. Right? If there's nothing in common, at least they're both divisible by 1. Okay? So similarly, least common multiple. That's the smallest, or not similarly, in the contrary, right? The smallest integer that is divisible by all numbers. Right, so notice the key difference here. The first one is the greatest integer that divide into all numbers, whereas this is the smallest integer that is divisible by all the numbers. Right, so of course, let's take 18, 20, and 30. Right, yeah, we can literally write out all the multiples out to infinity, and we eventually realize, oh, none of those numbers are in common. Right, 18 and 30, divisibles of 90, but 28 or 90 is not divisible by 20. But eventually we'll get to 180. So this is 180. What was your factor tree again? 18 is 9 times 2. 3, 3, 2. 20 is 5 and 4. 5, 2, 2. 30 is 5 and 6. 5, 2, 3. Now with least common multiple, now it's a bit easier to write them in their exponent forms, because what we do now is we take the factor with the highest power. Right, so we take all the factors, we multiply all the factors together, but we only take the factor with the highest power. So for power of 2, we get a 2 squared, highest power. Power of 3, 3 squared. Right? Because we have a 3 and a 3 squared. 3 squared is a higher power, so we'll only take that one. And with 5, they're both 1, so we can just take whatever one we want. And then we multiply those together. Okay, so 4 times 9 times 5. Just like that. Okay? So 21 is 3 times 7, 45. 9 times 5. Here's a smaller example. 21 is just that. 45 is 3 squared times 5. So take the smallest power, or it's the biggest power. Right, so 3 and between 3 and 3 squared, of course 3 squared is higher. We take that one. 7 and 5, they're both to the power 1, so we have to take those. So 3 squared, which is 9 times 5 times 7. 315, right? Look how fast that was. Okay, 38 and 42. Divided by 2. 19 is prime. Okay, so that's 2 times 19. Right, both have 2's, but we just have to take one of them, just the highest power. Of course, everything else is just to the power 1, but we still need to make sure to multiply them. 798. Okay. Next, again, just factoring as usual. Same step over and over. Very good practice. Right. So 28 is 2 squared times 7. 42 is 237. 63 is 3 squared 7. Okay. Take the highest powers. We have a 2 squared and a 2. So we take that 2 squared. 3 squared and a 3. So 3 squared. And we just have 7s across the board. Just take one of the 7s. Alright, that multiply to 252. Alright, last one. 2 times 5. What the heck was that? 4 times 8. 2 and 2. Okay. Alright, take the highest power. For 2, we have 2 to the power 5. 3, 5, and 11 are just by themselves. Okay, big number warning. Just like that. Okay, that's it. So, all we have to remember is with factor trees, we just keep dividing in the numbers until we get to all the prime factors. With the GCF, we take the factors that are in common with both numbers, and then we multiply together to get the greatest common factor. Again, GCF, we want the biggest number possible. LCM, we want the smallest number possible. Once again, we take out the prime factors, but instead, we multiply the factor with the lowest power together. Sorry, we take the factor with the highest power together, and then we just leave out all the other factors with the lower powers. Okay, but with that being said, that's pretty much it. So, good luck practicing.